Today we're going to look at some more ways we can build structures. And we're going to look at this thing called resonance. And what resonance does is it looks at a structure that contains one single bond and one double bond and lets us know where can we put the double bond. Does it matter? Sometimes it doesn't. So sometimes it's possible to have more than one correct Lewis structure for a compound. So if we have a molecule or a polyatomic ion that has both a single and a double bond, we're going to suspect resonance. Now, the important thing about these structures is to know we can change the location of the double bond. We're not going to rearrange the location of the elements that are in the molecule or the structure. So only the double bond can change positions, not the atoms. So the polyatomic ions, nitrate, nitrite, sulfite, carbonate, commonly will form resonance structures. So we'll look at a couple examples and you'll get the hang of it pretty quick. It's not too difficult. So here's an example of the nitrate polyatomic ion. So each of these structures is written correctly. If we look at the formal charges on each, we'll see they're identical. But as you see in each of these structures, the only thing that's changing is the position of that double bond. So let's try one. Let's draw a resonance structure for carbonate. So the first thing we need to do is write the formula for carbonate, and that's a polyatomic ion, and it's CO3. And we check its charge, and we'll see it has a 2 minus. So now we need to add up the valence electrons that we can use. Carbon is going to bring us 4, and we've got 3 times the oxygens, which will be 6. Then we have to go back and remember that that 2 minus means we have an extra 2 electrons added into the mix. So that's going to give us 24 electrons to satisfy octets and to make our bonds. So let's make our structure the way we think it's going to go. In this case, we're going to have carbon, and we're going to put 3 things coming off of it. So we've used 6 valence electrons. Let's go in and satisfy octets. Here's 8, 10, 12, 14, 16, 18, 20, 22, 24. Now each one of those oxygens is perfectly happy because they have their 8 valence electrons, but carbon's like, hey, what's the big idea? So we know by now that every element in a compound gets credit for the bonding electrons. So all we have to do is take 2 of these unshared electron pair and move them into the bond. So I'll do that here with this oxygen. So now we end up with a structure that looks like this. If we were to complete it, we would put the brackets around it and of course put that charge on the outside. But let's go ahead and draw the resonance structures for that. So we see we have the double bond here between the oxygen and carbon on the upper right, but we can also make it with the one on the left, or we could also draw it to the one on the bottom. So each of these structures is accurate and correct, and again you would have to show the charge on the outside of that structure. So there would be 3 resonance structures for the carbonate polyatomic ion. Let's look at nitrite. Now nitrite as a polyatomic ion has the formula NO2, and it has a -1 charge. Nitrogen we know is in group 5, so it's going to be bring 5 electrons. We're going to add those to the 2 times 6 for the oxygen, and we've got 1 extra electron that we get to add in there. So we've got 12, 17, 18 electrons that we can use to make our bonds and to satisfy octets. So let's put our nitrogen in the middle, and we'll bond 2 oxygens on either side. So we've used 4 electrons. Here's 6, 8, 10, 12, 14, 16, 18. All right, so each oxygen has its octet. Nitrogen is a little shy there with only 6 electrons, so it's easy to take 2 from an oxygen and put it into the bond. Now you can see where the resonance is going to come in. We'll go ahead and put this in brackets and put its charge on the outside, and we'll draw its resonance structure, which will be the double bond on the oxygen on the opposite side. So if we check formal charges, we're going to see they're identical, and none of those, not one is more correct over the other. So when we asked you to show resonance structure, you'll have to show all the possibilities that you can make with that double bond. Now we're going to look at some exceptions to the octet rule. And remember this from last semester, that when we were saying why do elements form compounds, and that was to become more stable. And we said what was more stable, and the most common answer is to have 8 electrons in your outermost energy level. So that's for most, but it's not for all. And we're going to look at some of these exceptions. Some molecules and ions do not obey the octet rule, and there's a couple reasons. One of the reasons are if you're adding up your valence electrons and you find out you have an odd number of valence electrons, you're not going to be able to obey the octet rule. So let's look at this example for nitrogen dioxide. This isn't the nitrate ion, this is nitrogen dioxide as a molecule. So its formula is NO2. Let's add up its valence electrons. We'll get 5 from the nitrogen plus 2 times 6 from the oxygens. That gives us a total of 17 valence electrons, which is an odd number. So right away we're going to know something strange is going to happen. So let's put our nitrogen as a central atom. We'll put our oxygens coming off to either side. And let's fill in the octets for the oxygen. So far we've already spent 4 electrons in the bonds. Here's 6, 8, 10, 12, 14, 16, and we've got one more that's left over. All right, so looking at this structure, and if we were to check the formal charges, we would see that this is not a very stable structure, a very common structure. So what we'll want to try to do is give nitrogen as many valence electrons as possible so we can bring in those electrons from, unshared electrons from oxygen. So let's draw the structure again. And we'll fill in those unshared electron pair. And that would be the structure. Now, if we were to do resonance, of course, you can draw the double bond on the other side. But in this case, we won't show any charges because there aren't any charges. Some compounds will form with fewer than 8 electrons in their outermost energy levels. And this isn't very common. This is usually happening with the little guys. So if we look at the molecule boron trihydride, which would be BH3, add up the number of electrons we can spend. Boron's going to give us 3. Hydrogen will give us, the 3 hydrogens will give us 1 each. So we have a total of 6 electrons. If we make our structure with boron and the 3 hydrogens coming off of it, as soon as we form the bonds, we've already used up all of our electrons, and boron ends up with 6 valence electrons. And that's just the way it is. Beryllium dichloride is another example. Beryllium, we know, brings in 4 valence electrons, and we're going to add it to the 2 times 7 valence electrons that the chlorine's going to bring in. So that gives us a total of 18 valence electrons. So we'll put our beryllium in the center, add the chlorines to the side. We've used up 4 of those 18 electrons in forming the bonds. We'll put the rest in 2, 4, 6, 8, 10, 12. I'm running out of room there. Come on, you. 2, 4, 6, 8, 10, 12, 14, 16. Sorry, guys, I made a mistake there. Beryllium only has 2 valence electrons. That's why that structure wasn't working. I was giving it the 4 from boron. So we have 2 valence electrons for beryllium plus the 2 times the 7 electrons from the chlorine. So that's going to give us a total of 16 valence electrons. 2 times 7 is 14 plus the 2. So we'll put our beryllium as the central atom, and then we'll satisfy the octets, and we'll see that we've used up all 16 electrons, and beryllium is only able to make 2 bonds there, so it only has the 4 valence electrons. So those are some of the exceptions. Now we're going to look at a different type of an exception, which is an expanded octet. Sometimes we'll see that elements will take in more than 8 valence electrons. So the ones to be suspicious are generally are phosphorus and sulfur. They have a tendency to be able to take in more than 8 electrons. So let's look at phosphorus pentachloride, for example. So phosphorus pentachloride, PCl5. Phosphorus we know has 5 valence electrons, and we're going to add that to the 5 times 7 valence electrons from the chlorine, and that's going to give us a total of 40 valence electrons to build our structure with. So we'll put our phosphorus as our central atom, and we're going to have 1, 2, 3, 4, 5 chlorine atoms coming off of it. So once we've made our bonds, we've used up 10 of those 40 electrons in the bonding. So let's go through and put in the rest of them. Here's 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. I think I miscounted somewhere. Let's see. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38. Here we go, 40. Yes, I miscounted. So now we see that phosphorus has these 2, 4, 6, 8, 10 valence electrons around that central atom, which is the expanded octet. Sulfur hexafluoride is another example, and I'll let you try that one. Also, I would like for you to try to draw the structure for Xena tetrafluoride and chlorine trifluoride. For homework tonight, it would be good for you to review and look at pages 42 through 48, or I'm sorry, do 42 through 48 on page 258 from your book. And I think Mrs. Ramirez is going to help you with some of these resonance structures. And I'd also like you to look back at a previous example I gave you on yesterday's lesson, looking at this Lewis structure for the phosphate polyatomic ion. And I want to know, is this the best structure for this polyatomic ion? Kind of play around with it and see if you can come up with something that's better than the example that was given. And maybe there'll be some extra credit in there for you. So look at that and give me reasons why you think that this is not the best structure. All right, I will be in tomorrow. The snow plows have made it through today, and so our roads will be plowed. So we can work on these together tomorrow. And I thank you for your patience in having to deal with video lessons rather than the real thing. And again, I apologize for the goofiness of some of these, but trying to do this at home, there are so many distractions, especially with three very, very helpful Siberian Huskies. I'll see you guys tomorrow.